Hi, this video is about problem solving the SQL way. And by SQL way, I mean telling SQL Server what transformations to make on sets of data to solve a problem, as opposed to telling SQL Server how to solve the problem step by step. All the SQL that I'm going to show you can find at the link below. And what's important to start out this video is the problem itself is not really important. We're really going to be looking at how we think about solving the problem and not really about the problem. So to start out with, let's look at the problem that's been solved, and that is multiplying numbers. What I have on the right over here is the normal typical grade school method for multiplying two numbers together. And what I've done on the left is repeated it in a binary form. This is just to set up our thinking about the logic that I'm going to show you. We're going to be thinking about the bits. And so when we do it in binary, when we multiply two numbers in binary, it's actually a little easier because essentially we're multiplying by 1 or 0, which means we're essentially copying the top number here for every one bit we have in the lower number. And of course, as we move over through the bits, we shift the top number over and then we sum, which is similar to the grade school method where we take the top number and we multiply the bottom number by each digit of the top number, and then as we do that we shift over and then we sum. So the algorithm I'm going to show first is an imperative way of doing it, which is to say that I'm telling SQL step by step how to solve this problem. But it's good to think about the binary form of this when you see this logic. So this is a SQL scalar function. And you can think of it almost like a VB program. I'm declaring variables. I've got some parameters coming into the function. I'm declaring some variables. I'm using a little SQL here to set those variables up. This little SQL here is essentially saying, even though left and right have come in, I want the right-hand side value, which is ultimately the right variable here, to equal the lesser of the two parameters coming in. And that's just a little bit of an optimization, because as we're looping through the bits, we want the looping to be as small as possible. So if this right-hand side is smaller, we'll be doing less looping down here. Okay? So the other thing that's going on in here is we're dealing with the sign bit. We're going to treat the numbers, even though they're signed, as unsigned, which means that if it's negative, that means that the most significant bit is turned on, which really means we want to look at it not as a negative value, but as a positive value. This is essentially what the most significant bit in a 32-bit unsigned number would be in terms of its decimal equivalent. So here we're dealing with a decimal 19, which is much larger, and we're essentially setting it to what the left and the right would be if they were unsigned integers coming in. So the algorithm's simple. While the right number is not 0, we're going to look at each bit, the least significant bit. If it's 1, we're going to sum the left side. But we're not going to let that overflow. This is essentially this mod operator here saying, I only want the lower 32 bits of this summation every time to go back into the result variable. So we do that when the bit is turned on the right side, and then what we do is we divide, which essentially pulls each bit in the right down to the least significant bit, and the floor lops off. The floor function makes sure I'm only talking about a whole positive number when I divide by 2 here. So as we're shifting the right bits down to look at them, we're also shifting the left bits up by multiplying by 2, and only taking the lower 32 bit. As this number gets bigger and bigger, we're lopping it off and only saying I want the lower 32 bits. And so this is essentially achieving this binary arithmetic here, this binary summing of the partial products. That's what's happening in this loop. And then when we're done, when we return the value, we're converting the most significant bit back to its negative equivalent, so that the integer going out, its most significant bit, will be set appropriately. So this is very much like I would solve this problem, say in VB, C#. So I would rather do this all in SQL, and I'd like to have an inline function, because inline functions are typically more efficient. They can be optimized in more ways than a scalar function like this can, because SQL Server treats scalar functions like this when they're applied in a SQL statement, like on a million rows. It will run each row through this and call this a million times, and to SQL, this logic becomes opaque. It cannot optimize this in any way in the query where it's being used. So let's take a look at an inline version of this algorithm. And here what I've done is I've created another function, but you can see it's returning a straight SQL result. We'll see how this is applied if you're not that familiar with inline versus typical scalar a little later. But ultimately what we're doing is we're doing similar operations. This select statement is very similar to this first select here, preparing the variables, getting the initial values. And then this bottom SQL here is very much like the end of this statement where I'm treating the sign bit. But in the middle, we have a curious thing going on. What we have is a recursive common table expression. So we're taking the initial values, which are setting up our left and right side, dealing with the sign bit, converting them into a large decimal number, and we're taking that in the anchor side of this. So a common table expression that's recursive has an anchor, and then essentially its union with the recursive side. The anchor is just getting us this first row out of here. And then the recursive side is working, calling itself, and then applying these transformations, which are essentially similar to what's happening in the for loop here. So where is the while? That's right here. While the right value is not 0, we're going to apply this transformation. Here we're saying is the least significant bit of our right value, is it on or off? If it's on, we're going to do the summation, take the lower 32 bits. Otherwise, we're just keeping the result as is. And then here we're doing the shifting up of the left side and taking the lower 32 bits. Here we're doing the shifting down of the right side. So essentially this is going to be recursive potentially up to 32 times, because we could have bits all the way up to the most significant bit coming in on both sides, so this can recurse from 1 to 32 times. So I haven't really changed the nature of the first logic. I've essentially just changed it into an inline function. I'm still kind of telling SQL how to solve this problem. So if I want to start thinking about how we would do this purely in sets, I need to go back to the drawing board and think of the numbers themselves as sets of bits. So in this example, what I'm doing is I'm declaring the variables and looking at some test values, and I'm still preparing the inputs, making sure the right-hand side is the lesser of the two values. But here I'm doing a funny thing. I'm taking every single bit that could potentially be in any one of our numbers here, and I'm essentially taking and creating a row for each bit, the least significant bit. to 2-bit, 4-bit, 8-bit, all the way up to the 32nd bit, which I'm still keeping this as an integer. I'm leaving that negative, but that is the 32-bit, and I've also got a little sign column here, which you'll see below. I'm using that sign column. So what I'm doing is I'm taking the inputs, and I'm essentially just joining the inputs across all these bits. And I'm saying, keep these bit records wherever they're actually in the right-hand side. So this is a bitwise compare. Take the bit value and bitwise AND it with the right-hand side value, and wherever I have a 1, essentially, wherever the bit is on, I'm going to keep that record. So let's take a look at what this looks like real quick. Okay. So what I have is I'm putting the right-hand side in here, I'm just multiplying it across. I'm just selecting it out with every row that I'm getting. And then here we're seeing the actual bits that were selected. So these values here, each one is a single bit, and it's in the right-hand side. So if I sum these, I should get this value here if these were all summed up. And then what we've done is we've taken, and right here, I'm dealing with the sign bit, and potentially I'm converting that to a decimal, and then in my second cross supply here, I'm multiplying that by the left-hand side. So essentially, this is doing all the shifting that was happening in, let's go back to our first imperative. All the shifting that was happening here is happening all at once across each one of these rows. So this is the value of the left-hand side shifted by each of the bits that was found in the right-hand side. And then here I'm just lopping off any overflow and saying I only want the lower 32 bits of that. So if I summed these and then lopped off the lower 32 bits and dealt with the sign number, that should be my solution. So let's take one example. Let's take this highest bit here and take a look at it in terms of the binary form. So this bit was found in here. It's the highest bit that was found in here. It equals 524 to 288. That's what the bit looks like in binary form right there. Okay? So that's this bit right here. And here is the left-hand side converted to binary form. So this left value shifted right here is essentially a copy of this shifted over exactly by this bit here. And then this is the lower 32 bits of that. Oh, excuse me. That's the lower 32 bits of it. So that is equivalent to that. Okay. So what I'm going to do is run this query along with, I'm taking that query down here, and I'm calling that query, this set of results here, I'm calling that partial products, wrapping that as a CTE, and then I'm going to sum those, cut off the lower 32 bits, and then I'm going to adjust for the sign bit here. But I'm going to show all of this together at the top query. Okay. So this is the first query, what we saw just a second ago. And then here is the second part where I'm summing it all together. So here is, this here was a sum of all of these bits. And you can see it equals our right-hand side. I took this value out. It's not necessary anymore in this lower one here. Here are the left. This is a sum of the left shifted values. All that is this sum here. And of course here it's not, this is going beyond 32 bits here. It's larger than a 32-bit number. So here it is, this is it truncated down to the lower 32 bits. that number truncated to the lower 32 bits. And then this here is the sum of, well, let me say this is all of these numbers, the lower 32 bit, and this is the sum of all of these, right? And this is that number, lower 32 bits of that number. So we're taking only lower 32 bits. And then this here is the sign adjusted result. So this would be the result of that multiplication if these were two unsigned numbers multiplied and then the sign bit was still treated as a sign bit. Okay, so this is giving us an idea of a different approach. It's still achieving the same thing, but we're not telling, we're just talking about transformations here. All the bits applied across the value. And so it gives us a different approach. So let's take a look at what this does for us practically. Let's take a look at what the function would look like now. So I have an inline function. There's no recursion going on. I get my left and right values in. I flip them around if the right is not the lowest one. It probably isn't necessary, but it makes the join smaller. Probably still is an optimization. The right-hand side will have less bits if it's the least if it's the smaller of the two values, and so when I join across this, I'll get less rows joined here if right-hand side is the smallest. This is probably still a good optimization. And here I'm just getting the product, getting the lower 32 bits of it, and then here I'm summing all of those together to get that sum, and I'm also taking the lower 32 bits of that sum because it has been converted into a large decimal. So I want to make sure that still we don't need any bits beyond the lower 32. And then here's the treatment of the high bit back into the sign bit. So this is essentially equivalent to our imperative version and an equivalent to our recursive version. So let's take a look at how these all perform. So here I'm going and doing statistics IO on and time on, so that whenever I run a query, I'll get the results. And I'm using this technique, this number generating technique, to generate 1,000,000 rows. And I'm applying those 1,000,000 rows 1 through 1,048,576. Each value is being multiplied by this to this number here. And I'm not going to run these for you. I've done a run. It takes a while. When I do this with just the regular scalar, the imperative scalar function, it takes about 50 seconds to run that. This is one of the times that I got off that. So 1,000,000 rows, we don't have any basis for comparison yet, but 50 seconds is that's some time. But we're doing it on 1,000,000 rows. It's pretty good, maybe, but we don't know. So I ran this test with the recursive version, same exact 1,000,000 rows, and then of course when you do it to an inline function, you cross apply. It's essentially running the same set of numbers through the multiply function with the same basic number that we're applying it to here. And then we ran this, and this was really bad. This came out to be 74 seconds of elapsed time, and it actually had to use a work table and do some logical reads and scans. So this was pretty bad in terms of CPU and total elapsed time. Much longer than. So even though this was more SQL-like and I used an inline function, it actually turned out to be more poorly performing than the imperative version, the scalar function. So here we go with the third one. What I did was I ran the same set of numbers through the non-recursive inline, and I got a much better result out of that. 10 seconds total time compared to 50 seconds, and CPU time was 30 seconds CPU time instead of 40 seconds. So much better results. And so this entire script, all of the examples, is at the link below, and hopefully it's given you a kind of a look at thinking through a problem differently because you're in SQL, and kind of a contrast between thinking in sets versus thinking in step-by-step imperative logic. Thanks for watching.